Greetings. This is Module 1 of 9 in the Introduction to Java Programming. My name is Tom Dunn, and I'm a software mentor for the first robotics competition. I've been a mentor for the last 11 years with Team 2028 and Team 3359 in the southeastern Virginia area. This course is going to go over the background and some of the fundamental principles behind programming in Java. It's not going to get a whole lot into the FRC specific aspects of programming and controlling a robot. Rather, it gives you a good foundation to build on. So this is a picture of the ENIAC computer. ENIAC was one of the first successful commercial digital computers. It introduces some things that I think are fundamental that we need to be aware of. The first is that the computer itself is made up of a large number of circuits, and each circuit is energized or de-energized by plugging a wire into one of the various patch panel ports. And you can see a number of these wires dangling down on the racks on the left-hand side of this photo. Obviously, there's some problems with this. Reprogramming the robot required that you actually physically unplug wires and move them to different ports and plug them back in. And debugging was a very tedious process of tracing individual wires from one port to another. Needless to say, you spent a lot more time actually programming the computer than you did executing the programs. But it introduces some fundamental truths about programming. Every CPU chip has a machine language. The CPU chip itself is made up of a number of different circuits that can be turned on and turned off, and the machine language is nothing more than a bunch of numbers, each of which energize or de-energize specific circuits in the CPU chip, which in turn turns on behavior or turns it off. The individual behavior can be adders, it can be loading values into accumulators, incrementers, all kinds of functions can be performed by these circuits. Another thing that should be pretty obvious, the machine language itself is very dependent on the hardware. Since the individual bits in the machine language instructions energize or de-energize individual circuits, different chips are going to have different circuits and therefore are going to have different machine language representations. The CPU chips tend to come out in families. Once a company's developed a chip, they'll go ahead and develop follow-ons to that chip that use a very similar form of machine language. And you've seen a lot of these families of chips probably in the electronic devices that you have access to. I'm sure you've heard of the x86 processors, the ARM chips that power smartphones, PowerPC, 68000, MIPS. Humans tend not to use machine language. Just like moving individual wires on the patch panel on the ENIAC, writing computer programs as a series of numbers is very, very tedious and hard for humans to get their arms around. So we developed assembly language. Assembly language is still hardware dependent, but it abstracts some of the concerns. Basically, the individual commands that form each machine language instruction are converted into a name, and individual locations in the code are replaced with labels. So it's a little more readable. One of the most important aspects of programming is the computer's memory. Every cell in a computer memory has a unique address. Generally, it starts at 0 and it goes all the way up to however much memory your computer has. That could be nowadays 1 or 2 gigabytes for a low-end smartphone, all the way up to 16, 32, or 64 gigabytes for desktop computers and laptops. Within this memory, some of it is reserved for the system to use itself. Other memory is unused, and that memory is known as the heap. The heap is memory that's available for allocation by your program. And that is a very important term as we get into programming in Java. So we're going to come back to that term again and again and again. So I've highlighted that in blue. Within the memory that is reserved for system use, the most common area is called the call stack, which is just known as the stack for short. The call stack will store the return address when we execute a subroutine so that the computer chip knows where to return to read the next instruction. So here's an example of assembly language and machine language. You can see on the far right-hand side the machine language representation of this very short snippet of code. The $sign before each one of the numbers just represents the number in hexadecimal. So you can see the number AD followed by 0A the AD is the instruction, and the 0A is a parameter passed to that instruction. The far left side of this slide, you can see that exact same snippet of code represented in assembly language. So instead of $AD, you see the instruction LDA. LDA, I happen to know, is short for load accumulator. So we're loading the accumulator with the number 10. And that instruction is stored at the memory address 0600. 0602 stores the instruction STA, or store accumulator, at the address 0800. So if we go back to the machine language, we can see that's 8D0008. So that stores whatever we just put in the accumulator, which happens to be the literal number 10, at memory address 0800. And so on and so forth. We load the accumulator with 0, store it in 0801. We then increment 0801. And then we decrement the memory address 0800. Then we have an interesting one, BNE. That's branch if not equal. And the address F8 means go backwards 8 bytes to the address 060A, which is our increment command. So what this is going to do is increment the value stored in address 060A 10 times, and it uses the loop counter, which we store in address 0800, to know when it's performed this loop 10 times. So we have one variable that counts up, and we have another variable that's counting down. Again, it's a very simple subroutine, but already you can see this is tedious, it's hard to read, and it requires a good amount of learning curve to get familiar with. So luckily, the computer engineers of the day have improved things. Okay, the call stack is the most important of the memory structures that is pre-allocated. The call stack stores information about the active subroutines. A subroutine is a section of code that you can invoke, and when it finishes execution, it returns to the same place it was called. So we need to store the memory address of the instruction that we're going to execute once the subroutine completes. So that information is stored in the call stack. We can also store additional data in the call stack. We can preserve register values so that the subroutine can make use of those register values. We can also store local variables and parameters to the subroutine. Maintenance of the call stack is critical to the proper functioning of the software. Luckily, we don't have to worry about the management of the call stack very much. For the most part, it's handled for us and it behaves well. We just need to know what the call stack is and what it's used for as we program in Java. So here's a short example of the call stack. Don't worry too much about the code snippet on the left, but I can tell you we have 3 subroutines. The first subroutine is main. We have it highlighted in green. We can see in main there are 2 local variables, x and y. Both of those variables have to have memory allocated to them. This subroutine then executes the draw square method. So we can see in the call stack, when main is executed, it creates storage within its stack frame. The stack frame is all the memory used for one particular subroutine. So we create storage for both x and y, and in Java both of them are initialized to 0. What happens when we call the draw square subroutine? When we call the draw square subroutine, it also creates a new stack frame on the call stack. And this new stack frame does not need to store any local variables because this subroutine doesn't have any. This subroutine then calls the draw line subroutine. When we call that subroutine, we create a new stack frame on the call stack to store the draw line and, most importantly, the return address of where we return to once it's complete. Again, this one doesn't have any local variables or parameters, so nothing else is stored in the stack frame. What happens when draw line finishes? It's going to pop its stack frame off of the call stack and return execution back to the draw square. Draw square is now complete, represented by this curly brace, so it's going to now pop the call stack frame for its subroutine off of the call stack and return execution back to main. Main then completes its execution and it pops its stack frame off of the call stack. So we can see the stack will grow and shrink as elements are pushed onto it and popped off of it. This is an important feature to keep in mind. Luckily, computer engineers have developed higher level languages so that we don't have to program in assembly language. A higher level language creates a program that's independent of the computer hardware. That makes the program easier to read, easier to write, and easier to maintain. But there's a trade-off. The program has to be translated into the machine language for the individual processor that it's going to be executed by. That translation either happens by a compiler before the program is executed or by an interpreter while the program is executing. The first high-level languages were designed in the 1950s, so they've been around for a very, very long time. Examples of high-level languages are Fortran, C, Pascal, BASIC. You may have heard of some of these languages. We'll definitely touch on the C programming language as we go forward. What high-level languages did is they enabled procedural programming techniques, basically taking a big complex job and breaking it up into subroutines. And each subroutine is smaller and more focused and can be individually tested and individually developed by different people. It also introduced data structures. So in a nutshell, a data structure is a chunk of memory that's going to keep all of the data about one particular thing in one place. So it makes things a little bit easier. So let's go back and look at that same snippet of code that I showed you in assembly language, only this time we're going to do it in C. Now, this syntax is the C programming language, but it's pretty similar to what we'll see in Java later on. So the first thing we do, we declare a variable, j. Then we declare a second variable, I. I is going to be the iterator. That's what I stands for. So that means it controls the iteration through a loop. Next, we initialize j equal to 0. The fourth line, we declare a loop, a for loop. The for loop has three parts separated by semicolons. The first is the initializer. So we're going to initialize the variable I to 10. We're then going to have a section that compares I to see if it's greater than 0. As long as I is greater than 0, we're going to continue in the loop. And lastly, every iteration through the loop, we're going to decrement I. That minus minus is a decrement operator. So I is going to start at 10, then it's going to decrement to 9, then to 8, then to 7, and so forth. Eventually, when it reaches 0, this clause will determine that it's time to exit the loop and we'll finish. Every time in the loop, we're going to execute all the code between these two curly braces. So we're going to increment j by 1 each time through the loop. So we start with j equal to 0, then 1, then 2, then 3, then 4, so on and so forth. After 10 iterations through the loop, j is going to be 10. So what is object-oriented programming? Object-oriented programming came along after high-level languages, so it can be seen as the next step after the high-level languages we just went over. Programmers define data structures just like they did with high-level languages, but they also define the behavior, the operations that modify those data structures at the same time. When we put the structures and operations together, that defines an object. And as they could with the data structures in high-level languages, objects can have relationships. They can have aggregation or composition as well as inheritance relationships. The aggregation and composition relationships define a has-a relationship, like a car has an engine. Inheritance defines an is-a relationship, like a crow is a bird. What makes object-oriented programming successful is that object-oriented programs are easier to maintain and debug than procedural programs. So everything is an incremental step over the layers that came before it. The high-level languages were easier than assembly. Assembly was easier than machine language. And now object-oriented programming is easier than procedural programming. So objects exhibit 4 principles: abstraction, encapsulation, inheritance, and polymorphism. And again, those are highlighted in blue. I'm going to come back to those again and again and again and again. Object-oriented programs were first developed in the late 1960s. There was an organization within Xerox called the Palo Alto Research Center in Palo Alto, California. So that's known as Xerox PARC. And Xerox PARC invented the first object-oriented language, Smalltalk. After Smalltalk, we've seen a number of object-oriented languages come along. Smalltalk, C++, Java, C#, Python. These are all examples of object-oriented programming. So what is an object? All real-world objects exhibit state and behavior. So how do we know what's an object? The thing that I found the most useful is to read the problem statement and identify the nouns that you find in the problem statement. Those are good candidates for the objects in your system. So in a first example, suppose we get the challenge and the team decides after reading the rules that we're going to build a robot that will drive across the playing field. It will pick up a game piece, drive to the goal, and deposit the game piece in the goal to score points. If we go over that problem statement and look for nouns, robot is a noun, so that's a good candidate for one of our objects. Playing field is a noun, so that's a reasonable candidate. Game piece is a noun, so that's a reasonable candidate. And lastly, the goal. The goal is a noun, so that's a reasonable candidate. The verbs in that problem statement, drive, pick up, and drop, those are reasonable candidates for some of the operations. We're going to go over that in one of the later courses for the FRC Java programming. Software objects model the real-world objects that they represent. They exhibit behavior, which means that they perform functions. They have state, which means that they have data members within their data structures, and they communicate with each other via relationships between objects. A class defines a contract or a specification, and all the objects that instantiate that class will have the same attributes and services. So the class defines a brand new user-defined type. It also defines its own scope, and we'll get into both of those a little bit later. This new type that the class defines restricts interaction and enforces boundaries, and we'll get into that a little bit later. Remember those 4 principles of object-oriented programming. So classes contain 2 major components. They contain attributes and operations. Attributes are the data members. So the set of all the attributes in an object define that particular object state. And the operations in a class or in an object define all the behavior that you can perform on that object. So what is abstraction? In a nutshell, abstraction is implementation hiding. What that means is the only way you can interact with an object is by the operations that have been exposed by that object. In the object-oriented world, abstraction is the process of generalization. Basically, you pull out all of the operations that are more general than the specific class's scope. So it defines behavior that is applicable to a number of different but related types. So that sounds confusing, but it's really not. So for example, we could have 2 different sensors on our robot that detect game pieces. One of those sensors could be a camera sensor, the other could be an ultrasonic sensor. The implementation behind them is very different. The camera sensor is going to grab a bitmap of the image and it's going to process that bitmap looking for our game piece. The ultrasonic is sending sound waves out and getting the return echo from those sound waves. So it's more of a sonar implementation. We could implement a method that's an abstract representation of both of those sensors, and that method could be find target or find game piece. And by pulling that out, by abstracting that method into a more generalized representation, we're limiting interaction to both of those 2 objects to only that method that we've pulled out. So that's an example of abstraction. So what is encapsulation? Remember with abstraction I said that was implementation hiding. Encapsulation is similar, but we're doing data hiding. The data within a class are made up of the attributes, the data members that define the state of a given object. So what we do is we put an access specifier on those data members to make them private. Then we provide operations that are going to allow the user of our class to access those data members. If the user wants to make changes to the data members, which changes the state of an object, they have to go through an operation that we define, and operations that change the data are called mutators. What's nice about forcing any user to go through a mutator method, it's also called a setter method, is we can perform data validation to make sure the state of the object is always consistent. That way we can prevent it from entering an undefined state. So remember, encapsulation prevents others from playing with your private parts. You don't want to let people play with your private parts. So what is inheritance? Inheritance implements substitutability. It creates an ISO relationship. I believe I mentioned that a few slides ago. So here's an example. A Ford Mustang is a coupe. A coupe is a car. A car is a motor vehicle. That substitutability means anywhere I need a car, I can use a Ford Mustang because a Ford Mustang is a car. The base class is the more general that provides some of the behavior and some of the data attributes. So in this example, motor vehicle is the base class to car. Car is the base class to coupe. Coupe is the base class to Ford Mustang. The derived class is the more specific behavior. The derived class inherits the behavior and state of their parent class. They can override inherited methods. A method is an operation. So if a base class overrides it, that means it's replacing the implementation that it got from the more generic base class with a more specific implementation. So that's overriding. And again, that's in blue. So we're going to come back to that again and again and again and again. Remember that. So derived classes can add new behavior. They can add new state. But every base class contract must be fulfilled. Remember, I said a class defines a contract. So if I derive from a more general base class, I have to satisfy all the terms and conditions of that contract. We can add additional items, but we cannot take anything away. So every derived class must require no more and promise no less than the base class. So what in the world is polymorphism? Polymorphism is the ability to take on many forms. So in C++ and Java, as well as some other languages, we implement polymorphism by using method overriding that I just covered in the last slide. So a child class overrides a method it inherited from the base class. It still has to satisfy the contract of the base class, but its implementation is different. So it's used when a reference to a parent class in an inheritance hierarchy is used to refer to a derived class. So that sounds murky and confusing. So let's go back to our sensor example. The actual implementation of the find game piece method in the camera sensor class is going to be different than the actual implementation in our ultrasonic sensor class. That means those two classes are polymorphic, which means the actual behavior that gets invoked when I invoke the find target method depends on which class has actually been instantiated, which kind of sensor I'm actually talking about. So that's polymorphic, and it's one of the most powerful features in object-oriented programming. So let's review the relationships. The has-a relationship, I touched on two terms earlier, composition and aggregation. Composition infers an ownership. So A owns B, which means that B has no meaning or purpose without A. When A is deleted, B is also deleted. So what does that mean? Suppose I have, I don't know, a car, and the car has a unibody chassis. When the car is put into a crusher at the junkyard and crushed into a cube, what happens to the unibody chassis? It gets crushed as well. It gets destroyed at the same time the owner gets destroyed. It has no purpose without its owner. So that's an composition relationship. An aggregation is a uses relationship. B can exist independently from A. So when A is deleted, B stays around. So what's a good example of that? Suppose I have a college with a bunch of courses that are offered at various times by various professors, and each course offering has a bunch of students enrolled into it. What happens if I delete a specific offering? Maybe not enough students enrolled by the deadline. What happens to the professor and to the students? Are they killed off? No, they're probably not. So the students and the professor have existence independent from the course offering. So the course offering uses the students and uses the professor, but it doesn't own them. Ownership can define directional navigability, and we're going to get into that in a later course. But for now, let me just leave you with the relationship between classes can be one-to-one, one-to-many, and they can also be unidirectional or multidirectional. So we'll come back to that later. Remember, this is just about laying the groundwork. So let's go over the object-oriented programming terms. So a class, what is a class? A class is a category of objects. Class is short for classification. It defines a contract that all instances of the class must adhere to. So what are the instances of a class? They're the objects. So if I make 5 course offerings in that college that I just talked about, each one of those course offerings is its own object. It has its own state. One of them might be held on Tuesdays and Thursdays. One might be held on Monday, Wednesday, and Friday. So that's the state of the object. But they're all course offerings. So the course offering is the class. So the class defines a unified set of operations and behavior that the objects can exhibit. We've talked about encapsulation. Encapsulation means we operate on the contract. We have no dependency on the internal representation. In fact, the only way to get at the data members that make up the object is to go through the getter and setter or the accessor or mutator methods. In abstraction, we're extracting out the common features. So we're performing implementation hiding, whereas with encapsulation, we're performing information hiding. So in this case, with abstraction, we take out the common features and move them up into a more generic base class. So what is a base class? That's part of inheritance. So inheritance defines an is-a relationship. So we can say that a class inherits some of its functionality and some of its data members from the parent class, the more generic parent class. And that allows us to create polymorphic objects. Polymorphic objects allow the behavior to differ depending on the actual instance of an object that is created. And the inheritance defines one type of relationship. The other type of relationship, a has-a relationship, can have either composition, which is an ownership relationship, or aggregation, which is a uses relationship. So that's pretty much it for this Module 1, which is just a real quick introduction into the programming history and the features of object-oriented programming. In our next module, we're going to get into the history of Java and why these things are so important to programming a first robot. Thank you for attending.